The deeper you descend into the ocean, the more alien the world becomes. It is a place where sunlight vanishes long before you reach the true abyss, where pressure rises to levels that would crush a human body instantly, and where life, shaped by millions of years of isolation and scarcity, transforms into something that seems more like a creature from another planet than anything belonging to Earth. The Mariana Trench, the deepest known point of the world's oceans, is not simply a geological feature. It is a boundary line between the world we know and a world that exists on the edge of physical possibility. And the reason creatures become stranger, more frightening, and more otherworldly with depth has everything to do with the brutal conditions of the deep sea and the relentless pressure of evolution. At the surface, the ocean feels limitless, but familiar. Light dances across the waves, and fish swim in patterns we understand. But only a few hundred meters down, the familiar world begins to collapse. Red wavelengths disappear first, swallowed by the water, turning the entire world blue. Most creatures near the surface rely on eyesight and color, on camouflage and speed. But evolution at depth takes a different direction toward invisibility, stillness, and sensory perception that human biology can barely comprehend. As you sink deeper, you enter a world where survival depends less on what you can see and more on what you can detect. Vibrations, faint electrical signals, chemical trails drifting through cold, heavy water. At around 200 meters, the light dims to twilight. Beyond 1,000 meters, the world becomes completely black. Sunlight has no power here, and so biological strategies shift. Eyes shrink or vanish. Skin becomes transparent or reflective to blend into the blackness. Bodies grow gelatinous to withstand pressure without wasting energy on muscle. The pressure at this depth is already 100 times greater than at the surface. Imagine the weight of a small car pressing against every square inch of your body. And yet, for the creatures that live here, this is normal. They are built specifically for this environment. This explains why their shapes often feel unsettling to us. They are not designed to be pleasing to human eyes. They are designed to navigate a world without light, without warmth, and with barely any food. Their jaws are oversized to capture anything that drifts by, because meals are rare. Their stomachs can balloon to many times their normal size to store food for weeks or even months. Many species develop teeth so long that their mouths cannot fully close, because evolution favors catching prey over being comfortable. These beings did not evolve for beauty. They evolved for survival in starvation, darkness, and crushing pressure. But even these deep zones pale in comparison to what lies deeper. The Mariana Trench plunges down nearly 11 kilometers, a depth where the pressure is over 16,000 pounds per square inch. If Mount Everest were placed inside the trench, its peak would still be more than a mile underwater. The creatures that live in this super abyss do not resemble anything from the surface world. Their existence is a scientific miracle shaped over millions of years by environmental forces that would destroy any surface animal instantly. As we descend through the mesopelagic zone, known as the twilight zone, we encounter creatures like the hatchetfish, whose silver bodies reflect even the faintest sliver of light. They appear ghostly and unnatural, their eyes bulging outward to capture whatever photons remain. But their shape is not designed for intimidation. It is designed for vanishing. If you looked at them from above, their narrow bodies reflect light downward. If you look from below, they reflect light upward. They are almost impossible to see. Then we reach the bathypelagic zone, the midnight zone, where darkness is absolute, and the creatures begin to shift into forms that truly unsettle the human imagination. Anglerfish drift through the black water, with a luminous lure dangling from their heads, created by colonies of bioluminescent bacteria. Their mouths are enormous, opened wide like traps, with teeth angled inward to prevent prey from escaping. Their bodies look monstrous, not because nature wanted to make them terrifying, but because evolution pushed them into a shape that maximizes survival in a world where food is scarce and fast movement wastes too much energy. The anglerfish's terrifying grin, its needle teeth, and its glowing lure are all adaptations to a silent, starless world. In this region of the ocean, bioluminescence is the closest thing to sunlight. Over 90% of the creatures living in the upper deep sea produce their own light, not to illuminate their surroundings, but to confuse predators, lure prey, or signal mates. Some flash bursts of blue or green in patterns so complex that no human could replicate them. Others, the truly eerie ones, use red light, invisible to most deep-sea animals. They use it to reveal prey without being seen, turning hunting into a one-sided game. At greater depths, the bodies of creatures become simpler and more gelatinous. Bone cannot withstand the pressure. Muscle is too energy-intensive. This is why deep-sea fish look soft, flabby, and ghost-like. Their muscles are barely functional because they do not need to swim quickly. The ocean currents move slowly down here, and most creatures float rather than swim. The pressure at these depths would crush the gases inside any normal body. So swim bladders, the organs most fish use to control buoyancy, disappear entirely. Instead, deep-sea creatures use oils, fats, and gelatinous tissues to keep themselves afloat. The deeper you go, the more the environment alters the rules of evolution. In the abyssopelagic zone, which stretches from 4,000 to 6,000 meters, temperatures hover around 1 to 2 degrees Celsius. Food arrives mostly from above, a slow rain of dead plankton, fecal pellets, and microscopic debris known as marine snow. Larger food sources, like whale carcasses, are unimaginably rare events that can transform the landscape for years, attracting hordes of deep-sea scavengers. These moments of abundance shape the evolution of the creatures here, pushing them to develop senses that detect even the faintest hint of decay from kilometers away. Among the strangest inhabitants of this zone are the amphipods, tiny crustaceans with transparent bodies that can grow far larger in the deep sea than at the surface. In shallow water, they are small and harmless. But at extreme depths, some species of amphipods grow to the size of a human hand, their bodies adapted to pressure levels that would flatten a submarine. Their size is a product of deep-sea gigantism, a phenomenon where low temperatures and high pressure slow metabolism, allowing individuals to grow larger and live longer. Gigantism is one of the reasons deep-sea creatures appear more frightening. Humans instinctively fear shapes that are familiar, yet distorted. A shrimp the size of a fingernail does not bother us. A shrimp the size of a cat does. But in the deep, gigantism is not a sign of aggression, just a consequence of the environment. Other creatures survive through the opposite strategy, becoming astonishingly small. Microbial life thrives even in the deepest parts of the Mariana Trench, surviving on methane seeping from the ocean floor or on minerals created by chemical reactions in the rocks. These microorganisms form the base of a food web that supports larger creatures. Snailfish, amphipods, bacteria-eating worms, each adapted to a world without sunlight. When we reach the hadal zone, the deepest region of the ocean, named after Hades, the adaptations become even more bizarre. This is where the pressure is so extreme that even proteins inside cells begin to change shape. To survive, organisms produce special molecules called piezolites, which prevent pressure from damaging their cellular structures. The existence of piezolites is one of the most extraordinary discoveries in biology. It shows that life can adapt to conditions once thought impossible. The typical image of a deep-sea monster, a creature with huge eyes, a massive mouth, glowing organs, and a body shaped by starvation, is a reflection of the evolutionary pressures of depth. The deeper the environment, the more severe the pressures, and the more distorted and alien life becomes. What humans interpret as frightening is simply evolution maximizing efficiency in a world with almost no resources. One of the most important reasons creatures get stranger with depth is the lack of predation. Near the surface, predators are fast, athletic, and strong. Prey must evolve to escape them. This keeps evolution moving towards streamlined bodies and functional shapes. But in the deep, predators rely on ambush or deception. They do not chase. They wait. They do not fight. They snag whatever drifts close enough. Without the selective pressure for speed or beauty, evolution drifts into extreme territory, producing creatures that seem grotesque to us, but are perfectly optimized for their environment. And then there is the psychological aspect. Humans fear what they cannot see or understand. The deep ocean is the most uncharted environment on Earth. More people have walked on the moon than have reached Challenger Deep. Our imagination fills the darkness with monsters because darkness itself is a kind of void where anything could exist. And in a way, the deep sea delivers on that fear, not through fantasy, but through forms of life shaped by forces we barely comprehend. As we imagine sinking deeper into the Mariana Trench, it becomes clear that the forces shaping life here are unlike anything on the surface. The crushing pressure fundamentally rewrites the rules of anatomy. At the bottom of the trench, the pressure reaches more than 1,100 atmospheres. This is not a pressure you merely endure. It is a pressure that forces every molecule of your body into a different state. If a human were dropped to this depth without protection, all gases in the body would collapse instantly. Lungs would implode, sinuses would collapse, and the ribcage itself would fold inward as though it were made of soft paper. But deep-sea creatures survive because their bodies contain almost no air and very few rigid structures. They are made of water, gel, and slow-moving proteins that bend rather than break. The very absence of hard tissue becomes a survival strategy. To understand why creatures become stranger with depth, you must imagine what evolution faces there. Darkness so complete that eyes are useless, pressure so intense that rigid bones become liabilities, scarcity so severe that meals arrive perhaps once a week or month. Under these conditions, life evolves toward extremes, toward forms that look monstrous only because they are optimized for a world that does not care about aesthetics. Consider the snailfish discovered at depths of nearly 8,000 meters in the Mariana Trench. With a body so delicate that it disintegrates when brought to the surface, these fish are translucent and ghost-like. Their muscles are soft and watery, yet perfectly adapted to the pressure. Their skulls are not solid. Instead, they consist of cartilage-like material that bends without breaking. Their digestive systems are simple because food is sparse. They eat whatever small crustaceans or marine snow they can catch, pressing the limits of what is biologically possible. To a human, these fish look fragile and eerie, but in the deep sea, fragility becomes strength. The lack of rigidity prevents internal collapse. Even the shape of their bodies, elongated, soft, with almost no visible structure, is a reflection of evolutionary constraints. The trench itself is shaped by tectonic forces beyond human scale. The Pacific Plate plunges beneath the Philippine Plate, creating the deepest known point on Earth. This subduction zone generates earthquakes, hydrothermal activity, and fissures where mineral-rich fluids seep into the ocean. These chemicals feed microbial communities that form the base of the food web in regions where sunlight cannot penetrate. Life becomes dependent on chemistry rather than light, a form of existence known as chemosynthesis. Instead of plants using sunlight to create energy, bacteria use hydrogen sulfide, methane, and minerals. These microbes, invisible to the human eye, play the role that forests and plankton play at the surface. Without them, no higher life could survive. This shift from photosynthesis to chemosynthesis marks one of the most important transitions in the deep ocean. Without sunlight, ecosystems become driven by the Earth itself. Hydrothermal vents, methane seeps, and serpentinization reactions within the crust release the energy needed to support life. At some vents, towering chimneys reach heights of 15 meters, spewing mineral-rich water at temperatures over 350 degrees Celsius. Yet only centimeters away, the water is nearly freezing. This contrast creates microhabitats where unique organisms thrive. Giant tube worms with red plumes that filter hydrogen sulfide, shrimp with heat-sensing patches instead of eyes, and bacteria that turn toxic chemicals into usable energy. Although the Mariana Trench does not have the same vent systems as the Mid-Atlantic Ridge, similar principles apply. The organisms that survive in its deepest regions depend almost entirely on microbial life and the constant slow drift of organic debris from above. Each piece of matter that falls, whether a decaying fish, a scrap of plankton, or even dust-like particles, becomes valuable. For this reason, many trench creatures develop grotesque feeding adaptations. The gulper eel, for example, possesses a mouth that can expand like a balloon, allowing it to swallow prey much larger than itself. Its tiny whip-like tail ends in a bioluminescent lure, glowing softly in the dark. In the black emptiness of the deep ocean, where shape and color vanish, a faint glow becomes irresistible. Another eerie inhabitant is the fangtooth fish, whose teeth are so large they must fit into special pockets in its skull to allow its mouth to close. Despite its terrifying appearance, the fangtooth is actually quite small, rarely more than 16 centimeters long. This contrast between appearance and reality illustrates how deep-sea evolution exaggerates features that serve specific survival functions. Large teeth allow the fangtooth to seize prey in total darkness, where it cannot afford to miss. The massive jaw increases the odds of a successful catch. To us, it looks monstrous. To evolution, it is efficient. But the deeper you go, the more pronounced these adaptations become. At depths beyond 6,000 meters, even the hardiest deep-sea species disappear. This region, the hadal zone, is home to organisms found nowhere else on Earth. They exist in trenches and subduction zones, isolated from one another like islands. This isolation leads to unique evolutionary lineages, each shaped by its specific trench environment. The Mariana Trench, being the deepest, hosts the most extreme examples. Why do creatures here look horrifying? The answer lies in the combination of environmental extremes and evolutionary isolation. Many animals in the hadal zone evolve elongated bodies, huge mouths, and sensory structures adapted to detect vibrations through water that is denser than at any other depth. Eyes become tiny or vanish altogether. Pigmentation disappears because color has no function in pitch blackness. Skin may become transparent, making muscles and organs visible through a pale film. To human perception, transparency and exposed anatomy evoke vulnerability and strangeness, triggering instinctive discomfort. But again, these features serve survival. Transparency helps reduce visibility to predators. Enlarged sensory pores detect prey long before it comes close. Soft tissues prevent structural collapse. The monstrous appearance is simply the visible reflection of environmental physics. One of the most fascinating aspects of deep-sea biology is the phenomenon of metabolic scaling. At extreme depths, organisms move slowly, grow slowly, and reproduce infrequently. A crab at 9,000 meters might live for decades, growing only millimeters per year. Some amphipods have lifespans far longer than their shallow water relatives. These long lifespans allow genetic mutations to accumulate gradually, creating lineages that diverge significantly from any known relatives. The creatures look different because they are, in a very real sense, living fossils of a separate evolutionary timeline. Pressure not only shapes morphology, it affects biochemistry. At depths like those of the Mariana Trench, ordinary proteins would not function. The extreme pressure forces water molecules into proteins, destabilizing them. To survive, hadal organisms produce special molecules, piezolites, such as TMAO, trimethylamine N-oxide. These stabilize proteins and prevent them from compressing. In shallow water fish, TMAO levels are low. In deep-sea fish, TMIO levels increase with depth. At the deepest points, these levels reach the highest concentrations found in any animals on Earth. TMAO is the same molecule that gives deep-sea fish a strong smell, and its presence at these levels creates physiological differences visible even at the macroscopic scale. When scientists examine the bodies of deep-sea snailfish, they find nearly no rigid bones in the lower skull. This is because, at great depths, bone density becomes a liability. Bone collapses under pressure, cartilage bends. Softness becomes survival. Creatures evolve to be gelatinous because gelatinous tissues compress smoothly without shearing or fracturing. When humans describe deep-sea animals as slimy, flabby, or amorphous, we are observing the direct consequences of a biochemical arms race with water pressure. What about giant creatures? The deep sea is home to some of the largest animals on Earth, like the giant squid and colossal squid, both of which dwell in depths that overlap with the abyssal zone. These creatures, with their elongated tentacles, enormous eyes, and mysterious behavior, have inspired countless myths. But they are not terrifying predators in the traditional sense. They use their size to avoid being eaten by sperm whales, their primary predators. Their massive eyes, among the largest in the animal kingdom, evolved to detect faint shapes and bioluminescent flashes in the darkness, allowing them to sense an approaching whale from far away. Humans find giant eyes unsettling, but in the deep sea, a giant eye is a necessity. Even more mysterious is the possibility that unknown species, larger, stranger, and more adapted to the trench depths, remain undiscovered. More than 80% of the ocean remains unexplored. In the Mariana Trench, direct exploration is exceedingly rare. Only a handful of submersibles have ever descended to Challenger Deep. Each time they do, they find species never seen before. The scarcity of exploration means that many hadal species remain invisible to science, living silent, slow lives in darkness, deeper than any human has ever experienced for more than a few hours. The human fear of deep-sea creatures is, in part, a fear of the unknown. Our eyes evolved for daylight. Our brains expect color, shape, and symmetry. When confronted with organisms that blur these expectations, creatures with translucent bodies, disproportionate jaws, glowing organs, or eyeless faces, our instincts react with caution. But nature did not design these creatures to frighten us. Nature shaped them to survive conditions beyond imagination. In the deepest parts of the trench, even fish disappear. The physiological limit for fish appears to be around 8,200 meters. Beyond that depth, the concentration of TMAO required to stabilize proteins would become so high that it would disrupt the function of the cells. This means that the very deepest parts of the Mariana Trench, Challenger Deep, around 10,900 to 11,000 meters, are inhabited mostly by microbes, amphipods, small invertebrates, and possibly gelatinous organisms that have not yet been captured. These creatures exist at the edge of biochemistry itself. At such depths, life becomes a whisper, soft, slow, almost ethereal. And yet, even here, evolution finds a way. Amphipods collected from the deepest parts of the trench have special adaptations that allow their exoskeletons to remain flexible under pressure. Their shells contain aluminum extracted from seawater, a chemical trick no surface organism uses. The aluminum forms a gel-like coating that protects their bodies from dissolving in the mildly acidic, deep sea water. This adaptation is so unusual that when Japanese researchers discovered it, they were astonished. The deep sea, they realized, is a factory for evolutionary innovation unmatched anywhere else on Earth. Even the sediment at the bottom of the trench holds secrets. Samples reveal fragments of microplastic and human pollution, showing that no part of the Earth is fully untouched. But deeper within the sediment are microbial communities millions of years old. Some microbes have been buried for so long that they exist in a state of barely detectable metabolism, taking perhaps centuries to divide even once. These organisms do not resemble the energetic life forms we imagine. They are life slowed almost to geological time. Humans often imagine the deep ocean as empty, barren, a void lacking complexity. But in reality, it is rich with biochemical drama. Each creature that exists here does so only because of a delicate balance of adaptations. Adaptations that can appear frightening, but are, in fact, perfect in their purpose.